Now we're going to discuss the light visibility through the smoke, or especially it will be through the smoke, but however it can be applicable for anything else. However, it is from John H. Clot. It is a book which is under ASHRAE, by the way, research. There is a definition of the visibility in meter, how many meter you can see in front of you. It is equal to probability constant divided by a specific extraction coefficient multiplied by MB, which is mass of particles. The mass of particles can be generated from the particulated yield, or it is usually named as yield. So when you know the yield of the smoke, multiply by the mass of the fuel, which is mean we are defining this fuel when it is burned, it is generating a yield, a particulate yield, which is generate some particles. While we know the yield of this one, which is, for example, for wood, it is 0.015. For the polystyrene or polystyrene, it is 0.06. And the masses of flow from the species itself, and we're going to discuss about the species interaction. This is the mass of fuel. Okay. By the way, okay, before it, we know the specific extraction coefficient if the flame is flaming or smoldering combustion. Okay, so if the fire is flaming or it is smoldering, it is the type of the fire. However, from it, so when this one visibility is high, this one should be slow. So for worst case scenario, you use this one. For case scenario, you can use this one. Okay. This one, you know, like this flames, and this one, it is just a translation from the English. Okay. Now, so this one, we know it. K, which is probability, proportionality constant, which is if you want to see some reflected surface, which is mean you have a light and the light is illuminated the wall, so you need to see the wall. This number is 3. If there is illumination itself, so like an exit sign, it is 8. Okay. Okay. Now remaining is this one. So yield we know it, and the mass of fuel we know it, so we can get it. So by writing we can get how much is S. But usually visibility in meter, we're not doing it a manual calculation, we do it based on the simulation. So how in the simulation you need to ensure that is you are having a species and you having CO2. So based on CO2 you can know from the reaction itself how much fuel is generating it. So the ppm of the CO2 is defining how much fuel has been burned, which is define how much this amount, which will define this one. So why the CO2 ppm increase, no visibility, it's not meaning the CO2 itself is making it invisible, no. But the point is we are checking what is the ppm of CO2, which is giving an indication more smoke has been reached to this area, which is more fuel has been burned to generate that smoke, which is have more particles based on this. So we can use this equation to get what is the visibility we need. Okay. Now, okay, how to check how much CO2 and etc. This will open for us the species and the reaction analysis. We will go direct to the example. It is a little bit chemistry, but let's go with it. Assume that you have a carbon and the carbon has been burned with oxygen and you have gain CO2. Put the atomic mass of the carbon, put the atomic mass of the oxygen, put the atomic mass of CO2. This should be equal. Take care that is the O2, it is 21% of air. So, of course, carbon is wood. So assume that is you have a mass flow rate smoke is generated from the fire. Okay, is equal to the mass flow rate of CO2, which is outcome, plus the nitrogen, which is coming, plus the air. Okay, this is as total. When we say smoke, it's not meaning clear CO2. Smoke is a mixture between the CO2 and the air. Okay, so that is why when you have a plume, when we have an application, that is we have an atrium and the smoke is here and the bloom start to get bigger and bigger to create a smoke layer. So here it is a certain amount of CO2 and smoke. Why when we go more up we need more exhaust? Because there is some air join with the smoke. Yes, the smoke concentration will be a little bit, but still the smoke will be a smoke. Okay, okay. So smoke is a combination between the air and the smoke result out from the reaction. Okay, so CO2 it is very can be calculated how much is a heat fire size, the heat output. Okay, the heat output, which is defined based on the application, is 5 megawatt, 2.5 megawatt, 1 megawatt, whatever. No, there's no 1 megawatt, but according to the code. Okay, so this is the fire size, how many megawatt, and you multiply by a molecular weight divided by the heat release. This is the total heat power, and the wood. What is the heat release by wood? So you get kilogram per wood. Multiply by this one, you will get what? How much CO2? This plus how much is N2. Okay, N2 is equal what? Same. This one divided by this one. How much is the heat? Multiply by molecular mass. Multiply by the percentage of the oxygen N2 in the oxygen, which is this percentage. Okay, this plus what? This plus we know that is in fire. It's not meaning if I need one O2 and here there is one fuel, so it is exact apple to apple. No, we are knowing that there is a mixing ratio. More air needed to be injected to have some of it only going to be burned, which is we name it as burning air ratio. For wood, it is happen to be 6. You need to be 6 times what you need to have burning, otherwise it will not burn. Okay, so this one, how much we got here, multiply by the area, the burning ratio of the wood. Okay, so it is 6 times of the fuel. Huh? This is fuel mass, like this, it's fuel mass. Okay, and you will get this plus this equal air. It is an assumption because of the molecular mass of nitrogen and molecular mass of oxygen. It is almost the same, it's 14 and 16. We can assume that the molecular mass, the full mass of air plus mass of here air plus mass of nitrogen is approximately mass of air. It can be approximated. And so smoke ppm is what we got here divided by total mass of air, what we have. Okay, so the ppm of the smoke of the CO2 inside the smoke is this one divided by this one. Okay, and the mass flow rate of the entire smoke is this one. Okay, okay, okay. So the last one, how to calculate what is the temperature of the smoke. Temperature of the smoke, it is very easy. I know mass of the smoke, the total CO2 plus all the air and nitrogen, and T smoke is equal T ambient plus Ks. Ks is equal 1 from NFBA. Convective part, it is from NFBA 0.7 from the total part, as 0.3 is a radiation. So the radiation will not heat the air. Divided by m dot smoke multiplied by Cp of the smoke, it is almost 1 like air. You will get temperature of the smoke at the smoke flame, or just after the smoke flame. Okay, so till here it is the species and reaction. We are going to continue the thermodynamic. We are going to continue about the thermodynamics, the heat transfer, the heat exchangers, the psychometric and cooling tower, and evaporation. There is here evaporation from surfaces between these two, refrigeration cycles, probability, and test results.